All right, let's take a look at the ratio test in lesson 22. The ratio test is going to be used when we have difficult cases. If we have some easier problems, again, don't use this. Use an easier comparison test or p-series, geometric, all those. But if we think about what's given here, 1 over n factorial, it's hard to pass. It passes the nth term test, but remember, just because it passes that doesn't mean it converges or diverges. 1 over n factorial is not geometric or p-series, so what do we compare it to? Well, it kind of looks like 1 over n, which diverges, but then it, kind of looks like 1 over n squared, which converges, but they're not close enough to this factorial to compare to. So when we have these difficult cases, we're going to use the ratio test, and the ratio test, all the way at the bottom here, compares the nth term with the n plus 1 term, so the term after it. What happens here is when we divide them, when we do the next term divided by the current term, if we get a limit that is smaller than 1, meaning that n plus 1 is smaller than n, that means we're decreasing, which means we will converge. If our numerator is greater than our denominator, meaning our term is actually increasing as we list them out, if we get greater than 1, it's going to diverge. And then if we get the limit as 1, it's inconclusive. Now notice this does have the absolute value here, so we want everything to be positive when we're testing our limits. So that's what our ratio test is. Do our next term divided by our current term. So if we come back to this 1 over n factorial, this is what our limit is going to look like. We're going to take the limit as n approaches infinity of whatever the n plus 1 is. So instead of n, we put n plus 1 over that given factorial. Now we're going to do like we did before with the limit comparison test. Instead of divide by this, we'll multiply by its reciprocal. And so we'll get n factorial over n plus 1 factorial. And to simplify this, I want us to think about what if n is, let's just say 4. I'm just throwing out a number here so we can see how this would simplify. On top, we would get 4 times 3 times 2 times 1. And on the bottom, we would get n plus 1, so 5 times 4 times 3 times 2 times 1. We can see that all of these would cancel, and this would actually simplify to 1 over 5. So what it canceled was all of the n factorials, but it left one more. So this simplifies to 1 over n plus 1. The factorials canceled out with all the n's that they had in common, and then it just left you with the n plus 1 there. So now when we do the limit as n approaches infinity, we get 1 over infinity, which equals 0. Our limit of 0 is less than 1, and therefore it converges. All right, let's take a look. Just a couple recap things. The direct comparison test, that's when we compared it to something we knew for a fact. So let's just say on this left side we had 1 over square root of 2n plus 1. That kind of looks like a p-series that we could compare to. It was easy enough, it was a 1 over. And so when we were given the direct comparison, we used our known convergence, so we knew 1 over square root of n diverges, so we put that on top over our given problem. Now with a ratio test, instead of putting the, or it's a similar thing, the given problem still goes on bottom, but instead of the comparison, we're going to put the n plus 1, because that's what we're comparing to, the next term. That one goes on top, like we just saw there. So maybe a better way of saying is, what are we comparing to over the given? That way there's just some consistency whether you're using either method. So let's see a couple more examples of this. Pretty much when you see factorials, think of this process. Just because factorials are tough in convergence and divergence. So the ratio test is an easy way to get rid of the factorial. Otherwise, all three of these, if you take a look, they are like just off, just hard enough where they're not necessarily geometric. We can't compare to something p. This middle one, maybe we could try the root test, but if we did this in the correct order, you wouldn't know the root test just yet. So all of these are just hard enough and just different enough from our base cases of our geometric and p-series that this would be a good time to use this ratio test where we use our n+1 term. So if we do that, the limit as n approaches infinity, we'll put our n+1 term on top. So this will be 4 to the n+1 all over n+1 factorial. And then we will divide it by our given. 4 to the n over n factorial. We can see that instead of dividing by our fraction, we can multiply by the reciprocal. And so when we simplify this, we can put this into one fraction. We can simplify this to 4 to the n+1 over 4 to the n times n factorial over n+1 factorial. I guess I put them as two separate fractions instead of one. But then we can see with our common bases of 4, we can actually subtract our exponents. So n plus the top exponent minus the bottom exponent, right, when you have same bases. And so this actually simplifies, our n's cancel out. This just simplifies the 4 to the first power, which is 4. We saw in the previous problem that our factorials cancel each other out, and that leaves us with 1 over just the next term. And so as we do the limit, as n approaches infinity, this will now turn into 4 times 1 over infinity, which is 0. So we can see that our limit here is 0. Because our limit is smaller than 1, we know this converges. Okay, so the process is actually very similar to what we've seen in the past with our convergence and divergence comparisons, but now it's just the n+1 term. All right, let's see this with our next problem. Again, you could try the root test on this one, and maybe, actually I could see it working, but again, you were not supposed to know that just yet. I taught those out of order. So we're going to try this with the ratio test. We're going to see what's happening at the n+1 term. So 4 to the n+1 over this n turns into n+1 times 3 to the n+1, which is the next term. And then we'll divide it by our current one. Or maybe by now you know instead of dividing, multiply by the reciprocal, but this is a good setup. The next term divided by the current term. Instead of dividing there, we'll multiply by our reciprocal. So n times 3 to the n over 4 to the n. Kind of like we did before, when we multiply these, we can put our common things over each other. And so we can put this 4 to the n+1 over this 4 to the n times, we'll take the n from the top and then the n+1 from the bottom times 3 to the n on top over 3 to the n+1 on the bottom. And then we still have our limit in our problem. We'll do some simplifying here. We can see that our top exponent minus our bottom exponent, again, just cancels those out. So this is 4. The limit as n approaches infinity, remember when they have the same power, we divide their coefficients, or L'Hopital. Either rule works, but this middle one, as we approach infinity, will actually be 1. And then this last one, when we do our like basis top minus that bottom, what this actually gets to be is n minus n will cancel out, but this is actually 3 to the -1, which simplifies to 1/3. So when we get our limit here, we get 4/3, which is greater than 1. Because of that limit being greater than 1, this series diverges. All right. Let's try number 4. It almost looks geometric, like so close. We see that 4/5 there, and we want to say it's geometric and that it converges because it's less than 1. But unfortunately, that n in the front makes this not work. So you can try our ratio test. In fact, maybe you want to try this one on your own and play the video. I'm going to pause here and I'm just going to get the setup. I'm not going to do any solving, but go ahead and see if you can set it up and then play the video to check out if your setup is correct. All right, there's your setup with the n plus 1. What's nice is we don't have a fraction over fraction, so we don't have to multiply by any reciprocals. So we are all set. Oh, and I'm sorry, I forgot the n plus 1 here. There we go. We are all set now to simplify this. So go ahead and simplify it and pause the video, and then you can play it and see what we get. All right, your final limit would be 4/5. That is less than 1, so it converges. All right, you are welcome to try 5 and 6, but we're going to end this video with 7, and then if you need extra practice from there, then we can meet on that. Okay, so this is an interesting one because it already looks like we have the n plus 1 term, but actually we want to see the one after this. So we still want to check n plus 1 wherever n is. And so our setup here will actually be n plus 1, so up top it'll actually be n plus 2 factorial over n plus 1 as a base to the 2n plus 1 as the exponent. All right, then we're going to divide it by the given, n plus 1 factorial over n to the n. This is a little challenge. See if you can try this on your own. If not, you can play the video and see the rest of this. Okay, also, sorry, this should just be an n plus 1. I was like combining like terms instead of replacing n with n plus 1. So there we go. Again, feel free to try it on your own, or you can play the video and see the work I set up. All right, so when you divide the terms, remember you can multiply by the reciprocal to get it out of a fraction over a fraction. When you do that, I'm just going to align the similar terms, the factorials over each other, and then the ones with the powers of n. Now with the factorials, n plus 2 factorial actually cancels out all the n plus 1 factorials. If you're not sure, just throw in a value for n and see what cancels, and then see what term is left. And actually it's only n plus 2. It cancels out the factorials. With the n to the n on top, that stays here, and this is actually a really tricky one. We're going to break up the n plus 1 to the n plus 1. Remember, anytime you add powers, they actually had the same base with separate exponents. So that denominator can break up into n plus 1 to the n with the same base of n plus 1 to the 1, because with your exponent rules, you could multiply those and then add their exponents. So this is actually a really tricky one, but I want you to see one that's inconclusive. Because what we do now is we take the highest exponent. Whenever the limit as n approaches infinity is the situation, we take the highest exponent, which in this case the n exponent. And when we do the powers, remember we take their coefficients and we divide them. So this is the coefficient of 1, this is the coefficient of 1. So this one is actually 1. Again, really tricky. You would not be expected to do this without me in class. But I just want you to see that sometimes we get an inconclusive, where we actually can't determine its convergence. Okay, whatever time you have left, use as a work day, and I will see you guys later.